Swayam Prabha. Digital India. Educated India.
Portion in flow boiling, so which is basically the flow regimes in different size tubes, and then how do we use correlations which are purely empirical based on experiments, because there is absolutely no rigorous theory to calculate the heat transfer coefficient during flow boiling, because even pool boiling you have seen that we rely on empirical correlations. So, flow boiling is even more difficult to use any theory for that. And so just look at, I have talked about, when you compare the size of the tubes. So what you see is as you reduce the size of the tubes, the flow regimes are quite different, right. In smaller size tubes, the number of flow regimes that you come across are also going to be much lesser. So in that sense it is good in one sense, it is more predictable, what flow regime you are operating in. At the same time you may have the added benefit of improving your heat transfer rates by doing flow boiling in these small size channels. So as I said, bubbly flow is something, these are all described in detail in this presentation. I am just going to quickly go over it. And then you have slug flow, and then you have annular flow. Within the annular flow there are of course some subtle differences depending on how the interface between the liquid, which is an annular film, and the core, which is the vapor, is. There is a wispy annular flow, then there is a pure annular flow, and finally we come to these flow maps. These maps are actually very useful when people do experiments on different size channels, and here this particular maps are coming from the case where you have an adiabatic experiment where you are mixing liquid and air in a T junction and looking at the different flow patterns. How do you basically recognize? Because you have a specific control for the velocity of the liquid and velocity of the gas. So once you see this kind of flow map where you see velocity of the liquid on one axis and velocity of the gas on the other axis, you know clearly it is a adiabatic flow map, because when you are doing an experiment with flow boiling, you cannot have an independent control of velocity of the liquid and the vapor. So you can do this only if you do a controlled experiment where the mass flow rate of the air and the mass flow rate of the liquid are mixed separately. Okay. Now what this maps tell you is, if I say keep the liquid velocity fixed at, say, let us say around 1 millimeters per second, and then I vary the vapor or air velocities from a very small value of 0.1 meters per second to a large value of up to 100 meters per second, what happens to the flow regimes, right. And as you know, if I increase the gas velocity, now intuitively you can imagine is if I increase the gas velocity in my tube relative to the fluid velocity, so what is going to happen? The size of these bubbles which you see, these should be growing larger in size, and therefore when you look at this, it mostly starts in the slug flow regime, because slug flow is relatively large bubbles, and then they go transition to a slug annular regime if I increase my air velocity much higher. Now if I keep the air velocity fixed and if I increase the liquid velocity, so I go into a bubbly regime because there are fewer air bubbles and I have more liquid core. So like this, you can do these experiments at different diameter of the tubes. If I go to smaller and smaller tubes, like for example 1 millimeter size tubes like this. So what do I get? The number of flow regimes are going to come down, and increasingly, irrespective of what is the velocity of the liquid, if I change the gas velocity, mostly it will be in the slug annular regime, very less in the bubbly regime. And if I go to micro channels, it is more controlled here. So you can see, irrespective of what gas velocity I use, if I use moderate liquid velocities, it is mostly slug or slug annular patterns. So I have very tight control of the flow patterns if I go to very small size channels. So mostly they are in either slug pattern or slug annular, and the reason I have told you, if you do this particular experiment, you will see that once you have a bubble, so they quickly grow through to the size of the diameter of the tube, and very quickly they go into an annular slug flow or an annular flow regime compared to a larger size tube. So, therefore, the number of flow regimes are relatively less, and if you go to some very small size tubes, you are mostly left with only two options, either it is a slug or slug annular. But whether is this an efficient flow pattern, the answer is yes, because generally if you want to have a very high heat transfer rate, you want to have a slug or slug annular. The reason being is, if you take this tube and you have a slug flow like this, so this is your bubble, vapor or air bubble, and this is your liquid film which is in the annular region, right. So, this is called the slug flow here. So, if this now grows to a point where the entire liquid core is vapor and only in the annular region I have liquid, so this becomes a pure annular flow. Okay. Now, why this is efficient is this thin film is actually very efficient in reaching very high rates of evaporation, because when I have a convective flow, so this liquid film is not going to be eliminated very easily, although the vapor bubble is large enough, but the evaporation is happening by means of a very thin film in the liquid region, and that is continuously fed by the velocity of the fluid. Okay. And the smaller the thickness of this film, the more rapid the evaporation rates will be. So, it will be more useful for improving the heat transfer rate, and this just because it is evaporating, this is not going to run out very fast, because there is a continuous supply of the liquid due to the advection that is bringing in. Okay. So, the thin film will continue to exist, but due to very high and rapid evaporation rates, you will get very large heat transfer coefficients. So, therefore, the slug flow or the annular flow regimes are actually sometimes very useful in terms of improving the convective and nucleate boiling.
Sir, occurrence of thin film between the vapor plug
And the surroundings.
and the channel wall.
Yes.
Depend on the fluid we are using.
Yeah, so that in this case, if your velocity of the liquid is adequately high, this should replenish your liquid film rapidly. So, that should enhance your heat transfer rate. If you do not have a very high liquid flow rate, then this may reach a dry out very soon. Okay. So, now there are two important mechanisms that are happening when you have flow boiling. One is dominated by what is called as the convective boiling, which is nothing but the movement of the fluid. So, this is actually dependent on mass flux, whereas the other effect is due to the boiling itself, which is the nucleation that is happening at the interface between the solid and the liquid. So, this is the nucleate boiling, and this is primarily dependent on the heat flux, right. So, therefore, the combination of these two mechanisms is going to augment your phase change heat transfer in a flow boiling situation. So, the convective boiling is important because it is going to give you a bulk motion, like what I was talking about, for example, the liquid film which is evaporating. So, this is going to continuously supply the liquid towards the liquid film if you have a convective component which is dependent on the mass flux, and at the same time dependent on your heat flux is the rate at which the nucleation can happen and nucleate boiling can be sustained. Okay. Now, this is a very nice curve here, which is taken from Carl Stefan's book on phase change heat transfer. So, here you have the heat transfer coefficient which is plotted as a function of the vapor quality. So, what it says is, if you have a nucleate boiling dominant regime, so you will see that the heat transfer coefficient is very lightly dependent on the quality of the vapor, and whatever mass flux that you are operating here, whether mass flux changes substantially or not, the heat transfer coefficient is not changing much. So, it is only controlled by the amount of heat flux that you supply, whereas if you look at the convective boiling dominant regime, which is this regime, so it is only controlled by the mass flux that you put in, and it is not controlled by the heat flux. So, therefore, as I said before, if you have nucleate boiling dominant regime, it is controlled only by the heat flux, whereas if you have convective boiling dominant regime, it is controlled only by the mass flux. So, when you are doing these experiments also, when you observe, you see that the two phase heat transfer coefficient in a nucleate boiling regime looks more or less constant with respect to the vapor quality. So, it is slightly decreasing, as you see here, slight decrease, but it is not much. Whereas in the case of convective boiling dominant regime, there is a substantial increase with respect to the quality. So, when you are plotting with respect to quality here, you see there is a substantial increase in the heat transfer coefficient. Of course, the final heat transfer coefficient is addition of these two. You have both nucleate boiling and convective boiling together, adding up and giving you the overall heat transfer coefficient. So, what happens to the pool boiling curve? See, you have the conventional pool boiling curve. Let us say you have something like this, you have heat flux versus wall superheat. So, this may go like this, it may reach the critical heat flux. Now, if I start increasing the mass flux in flow boiling, so this curves will be shifted such that my critical heat flux will be shifted towards the top. So, I can increase my critical heat flux more substantially when I increase my mass flux. Okay. So, when I increase the mass flow rate of liquid, I can actually increase the critical heat flux. So, that is beneficial because I do not achieve film boiling very quickly if I have higher mass flux. So, the important question is therefore, how do I measure or calculate what is the pressure drop or predict what is the total pressure drop during flow boiling in small size channels. So, this has been a lot of research in the last decade or two, because people have been working on small size channels and then they want to predict what is the pressure drop and heat transfer coefficients. So, if you look at the model, so one of the most generally accepted models is the overall pressure drop comes from different contributions. Okay, it is not as simple as just calculating the pressure at the inlet and outlet. When you are especially modeling this, you have to account for a lot of things. One is what is the contraction losses at the entrance of the tube, because in a small size tube, when you have small size tube, so you are entering from a very large aperture into a very small diameter, there is a substantial loss due to contraction of the fluid. So, therefore, you have a contraction loss which you have to account for at the entrance of the tube, and then there is a significant amount could be covered by only a single phase liquid, because once you start heating this channel, it is not going to immediately start boiling, because it has to reach the saturation temperature of the fluid at some location, and it will probably happen somewhere downstream, but from the entrance till this location it is going to be primarily single phase. Therefore, the single phase contribution also might be important, and then the two phase contribution starts. So, once the flow boiling happens, then there are two phases. So, then you have to calculate the pressure drop due to the two phase. Then there is something called as acceleration pressure drop, because if you have large amounts of vapor, the vapor is going to move much faster than the liquid, and there is an acceleration component which will induce additional pressure drop. Then there is a gravitational component. This depends on the size of the channel. If you have a very small micro channel with a very small bond number, then the gravitational pressure drop may be insignificant, and then finally you have the expansion. So, finally the flow has to come out again through a very large header, right. So, this manifold will be very large, again there will be a large expansion loss. So, therefore, the total pressure loss, because when you are measuring the pressure, usually we put a pressure tapping at the inlet header and the outlet header. So, when we measure this pressure loss in an experiment, and when you want to compare it with the theoretical model, this pressure loss will include all these losses. One is the contraction loss at the inlet, expansion loss at the outlet, and again within the tube you will have a single phase pressure loss, then you have a two phase pressure loss which is accounting for the flow boiling, and then you have gravitational and acceleration pressure losses. So, for all this I think it is very difficult to find exact theoretical models, but we have a number of empirical models. So, I am just going to give those equations. For example, pressure loss due to contraction. So, we just use an empirical model like this, where your psi depends on what is the quality of vapor. If of course there is no vapor, if it is only liquid, your x will be 0, your psi will become 1, and this becomes the pressure loss that you use in single phase liquids. Similarly, now when you have a single phase pressure drop, there is a region which is only occupied by only liquid. So, in that case how do you calculate the pressure drop? So, you use standard correlations which are developed for micro channels or mini channels, which are functions of the aspect ratio of the channel. That means, if your channel need not be always circular in shape, but they can be some kind of a rectangular cross section. So, these cross sections can be of different aspect ratios. So, depending on aspect ratio, so this is B and this is A. So, depending on the aspect ratio, people have for example, Shaw and London, they have given a correlation for the single phase friction factor as far as rectangular channels of different aspect ratio is concerned. Okay. And similarly, now when you are talking about single phase pressure drop, again there may be a portion which will be actually developing, there is a developing length and the fully developed length. So, the boundary layers are merging and then it becomes fully developed. So, this developing length also has to be accounted for. So, people use this kind of Hagen-Bach's factor as a function of the aspect ratio to account for the developing effect of developing length. So, therefore, the overall pressure drop will be both the developing length pressure drop plus the fully developed frictional factor pressure drop. Then the exit pressure loss is also given by an empirical model like this, which depends on the quality of vapor at the exit, and then you have now the most important contribution is the two phase pressure drop, because once flow boiling happens, what is the contribution of the vapor and the liquid to the overall pressure drop is given by the two phase pressure drop. So, the two phase pressure drop is calculated based on the pressure drop of liquid alone multiplied by what is called as a two phase multiplier. Okay. This two phase multiplier is a function of this x, and what is this x? This x is nothing but the Martinelli parameter. So, remember, so we looked at what is Martinelli parameter. So, this is the ratio of pressure drop only when you have liquid divided by pressure drop only when you have vapor, and that is used to calculate the two phase multiplier, and finally what is the frictional pressure drop. So, I am just giving all these equations so that you can go through and use them in the calculation.
In the expression, Chisholm
Yeah.
expression,
Yeah.
C upon single x and plus 1 upon x square is coming. Here Martinelli is 1 upon x square.
Yeah, you have to take square root of that, exactly. So, this is x square is this, so x will be square root of this. Yeah. So, then you have expressions for gravitational pressure drop, you have acceleration pressure drop, so you just have to use them, and finally predict pressure drop as a function of the vapor quality. So, finally for heat transfer coefficient, again you have a very famous correlation which is given by Kandlikar. So, he has classified for Reynolds numbers which are above 100, he has classified that this will be primarily in the convective boiling dominant regime. So, he has given two correlations, one for nucleate boiling, one for convective boiling, and depending on Reynolds number, if the Reynolds number is very large, it is dominated by convective boiling. So, only this correlation will be used. Okay. And if your Reynolds number is below 100, then it is dominated only by nucleate boiling, then you use only nucleate boiling correlation. So, then there are some more parameters which are like this parameter f, which can be obtained for different working fluids. Okay. And this is the final plot of that correlation. I think that completes flow boiling. So, what I will do is I will quickly, we have some time, I will display a tutorial. You can see how to solve this problem. I have the solution also displayed here. So, you can try to go through some of the steps, and anyway I am also uploading this tutorial along with the PPT later on. So, you can watch it later. So, the first problem is basically pool boiling. Okay. So, there is a polished copper surface and you have water at 1 atmosphere pressure which is boiling, and assuming that the nucleate boiling happens at 6.5 Kelvin, this is the onset of nucleate boiling. find the corresponding nucleate boiling heat flux. So, how do you calculate that? So, this is using the Rosenhaus correlation, okay. And after that calculate the critical heat flux. So, you have the correlation also for critical heat flux. So, you just have to substitute these thermophysical properties and calculate what is the critical heat flux. You see here the onset of nucleate boiling happens at 73,000 watt per meter square, whereas the critical heat flux is at 1.2 million watt per meter square. So, this is much higher than what you see generally in the onset of nucleate boiling. And finally, what is the heat flux corresponding to the Leidenfrost point, that is the minimum heat flux. Again use the correlation for Leidenfrost heat flux, and that will give you the value, and there what is the value it comes to be 19,000. So, it is much smaller than the onset of nucleate boiling, okay. So, this is one problem. These are just standard correlations, you are just substituting the numbers and finding out the heat flux values, okay. Now, the second problem is flow boiling. So, whatever we have discussed, all the correlations I have shown with respect to pressure drop and heat transfer coefficient. So, you can use that here. So, you have a rectangular microchannel heat sink, okay. The dimensions are 1000, that is almost 1 millimeter by 50 micron. So, it is a very high aspect ratio rectangular microchannel, and then here we have heating on all 3 sides, but the top is not heated. So, these 3 sides are heated, top is unheated. The inlet temperature of the water is 70 degrees, the Reynolds number in the channel is 600. So, all the flow conditions are given. The quality of the steam corresponding to this heat flux is 0.055, which is at the exit of this microchannel. So, the initial 10 mm length has single phase liquid, and the total length of the channel is 20 mm. So, everything is given. So, 10 mm of this microchannel is only single phase, then remaining 10 mm has 2 phase flow, and your overall heat flux is this much. The exit vapor quality is 0.055, which is not very high, by the way. So, you are asked to calculate what is the heat transfer coefficient at the exit corresponding to this vapor quality, and what is the pressure drop for the entire microchannel. So, how do we do that? As I said, now you have to calculate the heat transfer coefficient due to convection boiling, due to nucleation boiling. These are coming from the Kandlikar correlation. So, each of this, for example, heat transfer coefficient due to nucleate boiling is a function of the convection number, the vapor quality x, and this parameter boiling number, and the vapor this parameter F1. So, for the given fluid you have to calculate what is the convection number and your boiling number, and for the given quality of vapor x, you know what is the value of heat transfer coefficient. So, the x value is given, that is 0.055, and convection number you have to calculate for the given vapor quality, boiling number also you have to calculate, okay. And once you substitute, the heat transfer coefficient for the 2 phase system is the larger of these two. Obviously, if you have Reynolds number which is above 100, automatically it is dominated by convection boiling, but in any case, to be on safe side, you can estimate both nucleate boiling and convection boiling values and take the larger of that. So, if you do that, here you are getting for the nucleate boiling, it is H is 8.3 into 10 power 4 watt per meter square Kelvin for the nucleate boiling. For the convection boiling, it is coming 1.7 into 10 power 5. So, the larger value is 1.74. So, that will be the heat transfer coefficient for the flow boiling. So, this is basically how it is usually estimated. You estimate both nucleate boiling, convective boiling, and take the larger value, because these correlations have both contributions anyway. It is not like yeah, it's actually, that's why finally it comes out that way. We can straight away do that, but you can always calculate both and check whether this is making sense, because if Reynolds number is very large, automatically it should be governed by convective boiling. But generally, if you look at these correlations, they have functions of both convection number and boiling number in both these, both nucleate boiling and convective boiling. So, the effects of both boiling that is nucleate boiling and convection is already incorporated in both these correlations. So, it is not like the nucleate boiling dominant correlation will have only effects of nucleate, so you should not add them, that is what I am trying to say. It is not like simply addition of this plus this. The reason why we are taking maximum is each of this correlation has separate effects of convection regime as well as the boiling regime. So, both are added already. Only thing this correlation is applied only when there is a dominance in nucleation boiling, and this second correlation is applied only when there is a domination of convection boiling. So, you have to find out which regime is dominant. If the Reynolds number is greater than 100, it is usually dominated by the convection boiling regime. Yeah. So, or the larger value of these two should be a guideline. So, the next part of the problem is pressure drop, and again the pressure drop is actually more complicated than heat transfer coefficient, because you have contribution from all of them. So, you have initially single phase liquid. So, you have to calculate what is the developing region there and the contribution of frictional fully developed frictional delta P. Then in the two phase region you have to calculate the two phase pressure drop. If there is any expansion or contraction losses, you have to account for that, and finally if there is any acceleration pressure drop or gravitation. So, therefore, pressure drop is the most complicated parameter even compared to heat transfer coefficient.
This data will help you to know the pumping power, pressure drop.
This is important because you are going to design your pump according to handle this kind of high pressure drops. Okay. So, I think you can go over this. I am going to put this along with the other slides, so you can go over the details of the calculation. If there is any doubt, we can discuss tomorrow also. So, the third problem is on condensation. So, I think this is very straightforward. You have a film condensation, laminar film condensation, which is happening on a cold substrate here, and the temperature of the substrate is given, and the saturation temperature of steam is also given. You are asked to calculate what is the mean heat transfer coefficient over the length of the surface. So, for that you use the Nusselt condensation theory and substitute all the thermophysical parameters, and after that you are asked to calculate what is the condensation rate. So, how do you calculate condensation rate? Because whatever latent heat of vaporization it is taking has to be taken out through the plate at steady state. So, therefore, your Q dot that is going through the plate has to be equal to m dot into h of g. Okay. So, that is the latent heat of condensation that has to be carried out by the plate. So, you equate these two and then calculate what is the mass flow rate of condensation. And the final part is what is the maximum velocity of the condensate. So, you have the velocity profile from the Nusselt condensation theory. So, you calculate what is the location of the maximum velocity. According to this, at y equal to delta will be the maximum velocity. So, you know the delta also. Delta is also given by the Nusselt condensation theory. You substitute, get the value of delta and put at y equal to delta, and you will be able to get velocity as 0.13 meters per second. Okay. So, this is just a basic tutorial which will tell you how to use all these correlations that I have given in pool boiling, in flow boiling and condensation in a practical situation. And as you can see, most of it is empirical. So, we do not have very rigorous theory which is derived specifically for each of these situations, right. Entire phase change heat transfer relies on the use of such kind of empirical correlations, and most of it is coming from experimental studies. Okay. It is basically plotting. So, as you see when you are having this flow boiling, right from single phase liquid, now you are boiling somewhere and you have this nucleation bubbly regime, and then finally it may be, depending on the size of the channel, you may have a sufficient length for bubbly regime, and then you may have a slug flow and annular flow. If it is a micro channel, then this may go to annular flow very quickly, right. So, if you are measuring what is the temperature of the wall as you maintain the heat flux along the length of the tube. So, this is actually the plot. The higher temperature here shows what is the surface temperature of the wall along the length of the tube, and the temperature at the below the surface temperature is telling you what is the mean liquid temperature. So, as you can observe, before the onset of nucleate boiling, when there is a single phase liquid, the slope of this line is like this for the surface temperature. Then the surface temperature shows a very small drop once the nucleate boiling happens. Locally there is a enhanced heat transfer, so the surface temperature shows a small drop, and then from there it continues to increase slowly till the boiling happens in such a way that slowly the dry out is happening somewhere at the exit. Similarly, the response for the mean liquid temperature also shows continuous increase, because you are adding heat to the fluid continuously as you go along the tube length. So, therefore, the mean liquid temperature also continuously increases. So, at some point I think the temperature difference between the wall and saturation reaches some horizontal value. So, there you see that slowly it is reaching a vapor quality which is kind of saturating, it is not changing further. So, depending on that, then these temperatures also stabilize. No, it can never happen in this case, because because you are controlling the heat flux. So, you are continuously adding heat to the fluid as well as the surface. So, the wall temperature also will slowly increase, although it may reach some kind of, it looks like it is saturated, but it is a very small increase because you are continuously adding the heat, but this will never reach the wall temperature, because fluid is also continuously heated.
One more thing, we have not talked about departure from nucleate boiling and dry out difference, or is there, or
In the case of what, flow boiling?
yeah, in the case of flow boiling.
Yeah. See, there is a dry out that can happen. These are of course adiabatic two phase flows, but when you are looking at this kind of flow boiling two phase diagrams, so if you are continuously adding heat and you have very long tube lengths, inevitably you will have to reach the dry out.
Yeah, but there is a term also which I have read, but I have not understood, the departure from nucleate boiling, DNB.
Yeah, so see, in flow boiling what we do is we plot of course the boiling curves, but also what is important is the vapor quality. So, you know for sure, if you have, for example, in the problem that I was describing, your vapor quality is like 0.055 at the exit. So, definitely it is not anywhere close to dry out. So, by measuring the vapor quality, you will be able to give a more quantitative understanding of whether it is close to dry out or not. If the vapor quality is very large, then you know that somewhere it is going to a dry out state. So, in flow boiling it is a little bit difficult, because in pool boiling, once you draw the pool boiling curve, you know that critical heat flux it has achieved, and after that it is going to go to film boiling. But in pool boiling you cannot do that, it is continuously moving and the vapor quality is varying. But if you measure the vapor quality somewhere at the exit, then you will be able to give a more clearer picture whether it is close to dry out or not. Yeah. So, it is measurement of vapor quality which is more important.
Maximum value is what, right?
Yeah, maximum value will be 1, but most of the times it will be like 0.1, 0.2 like that. So, by measuring vapor quality, you will be able to quantify whether it is in the nucleate boiling regime or is it going to the flow boiling, film boiling for example. I think film boiling will not so easily happen in flow boiling situation, because you are always continuously supplying fluid and the convection effect. So, there is always a Taylor slug flow that is going to promote a thin liquid film, but it will not completely evaporate to the extent that you see in pool boiling and cause vapor blanket. So, there will always be a continuous supply of liquid film. So, slug flow will be dominant for sure, as I showed, the flow patterns clearly show that in microchannels the two dominant flow patterns are slug flow and annular flow. So, that is going to be dominant, but you do not end up with film boiling so easily there. Yeah. Okay. So, I hope